Welcome back, students, to Chemistry Unit 5 and 6, the mole and analytical chemistry. In this lecture, we'll talk about molar conversions, Unit 5.2. Now, last class we talked about what a mole was. Remember, a mole is a representative amount of particles. It's a word that represents a number, like a dozen represents 12 and a pair represents 2. A mole represents 602 sectillion, or 6.022 times 10 to the 23rd. So if you have 1 mole of any compound, 1 mole of, say, water molecules, you would have 6.022 times 10 to the 23rd molecules of water. Or if you had half a mole would mean that you have half of 602 sectillion. So 6.022 times 10 to the 23rd divided by 2 would mean that half a mole was 3.011 times 10 to the 23rd. You can use the mole as a conversion to say how many atoms, molecules, particles, or ionicals you have. With that short little review, you are able to go in the other direction. If I have some number of molecules, how many moles do I have? This would be like saying if you have 36 eggs, how many dozen do you have? Pause the video and complete note quiz question 1 for lecture 5.2. Before we get too much further into this unit, we need to be able to understand what chemical formulas mean. When you have a chemical formula like H2O for water, what does each part of that formula represent? We've already talked about elemental symbols, that H stands for hydrogen and O stands for oxygen, but now it's time to talk about the numbers you'll notice in chemical equations. So first off, the little numbers, these subscripts. Subscripts tell you how many of each atom or groups of atoms you have. In the case of water, H2O, this 2 tells us that we have 2 hydrogen atoms in water. And if there's no subscript, it's understood that there's a 1. So H2O means that there is 1 oxygen. The subscript applies to what is directly in front of it. So water is H2O, hydrogen peroxide is H2O2, meaning hydrogen peroxide is 2 hydrogens and 2 oxygens. If we have an ionic compound with polyatomic ions, subscripts can be distributed in. Subscripts apply to what is directly in front of them. So in ammonium phosphate, there are 4 different elements here: nitrogen, hydrogen, phosphorus, and oxygen. If we were to take stock of all the elements in this compound and say how many of each atom is present in a formula unit, we would look at the subscripts. And we would say you have 1 nitrogen, 4 hydrogens, 1 phosphorus, and 4 oxygens. However, this 3 after ammonium means that you needed 3 ammonium ions in order to balance out the charge of 1 phosphate ion. So that 3 effectively distributes into these parentheses. So you actually have 3 nitrogens and 12 hydrogens in ammonium phosphate. You may also find that we will sometimes use coefficients. Coefficients are large numbers in front of molecules that apply to the whole molecule. At some point in this class, we may need 2 water molecules. 2 water molecules means that we need 2 whole waters, like this image shows. So needing 2 waters means that we would need 4 hydrogen atoms and 2 oxygen atoms. So coefficients apply to the whole compound. If I needed 5 formula units of ammonium phosphate, I would simply take our atom inventory of ammonium phosphate and multiply the whole thing times 5 to find that we would have 15 nitrogens and 60 hydrogens, 5 phosphorus, and 20 oxygens. Atom inventories will become important towards the end of this unit when we talk about balancing, and it will also matter as we move through today. With that being said, you're able to do number 3 and 4 on your note quiz questions. For number 2, keep in mind that due to the law of conservation of mass, if I start a reaction with 4 phosphorus atoms, the reaction has to finish with 4 phosphorus atoms. So using that logic, what number would have to go where this X is in order to give you 10 oxygen atoms? Go ahead and complete note quiz questions 2, 3, and 4, and then pause the video and complete page 9, taking an atom inventory of all the elements in each one of the problems on page 9. Now, not everything weighs the same. If I have a bowling ball and a feather, you're smart, you're pretty, and gosh darn it, people like you, you could probably tell me the bowling ball would weigh more. If I said I have 100 bowling balls and 100 feathers, which one weighs more? Again, it's still the bowling ball. Bowling balls weigh more no matter how many you have. So whether I have 100 or 602 sectillion, either way, a mole of bowling balls would have a much greater mass than a mole of feathers, because a mole is simply a number of them. So if I have a mole of carbon and a mole of lead, which one weighs more? You might remember from Unit 1 that the mass of each atom is given to you on the periodic table as the decimal place at the bottom of the tile in this case. That decimal place is in atomic mass units, it's relative to one another, but in this case, lead weighs more. Lead has a mass of 207 versus carbon with a mass of 12. So lead is far more heavier. Every atom of lead would weigh more. Now, where those weights come from is a bit of a long story. A long time ago, we used hydrogen as the basis for the mass of elements. However, the way that we determined the mass of elements was relative to one another. We would essentially remove the element from a compound and find the difference in the mass. In order to remove an element, it has to be present. Hydrogen, unfortunately, does not bond with everything on the periodic table. It doesn't bond with metals, at least not readily. And metals make up a vast majority of the periodic table. So the use of hydrogen was not the most practical use. So we started using oxygen in the late 18th century. However, around the time that Rutherford conducted his experiment, it was determined that oxygen has a couple different varieties. Most oxygen is oxygen 16, however, there's oxygen 17 and oxygen 15, and because of that, basing our mass off of oxygen became slightly problematic. So in 1960, the International Union of Pure and Applied Chemistry convened and decided to use carbon-12. They said the isotope of carbon, carbon-12, they would use as the basis for the mass of elements. So to make math easy, what they said let's accumulate 12 grams of carbon-12 and figure out exactly how many atoms of carbon-12 that is. And using some complicated math and experiments, they determined that it was 602 sectillion, or 1 mole. That's where this number of the mole came from. It came from how many atoms of carbon-12 it took to make 12 grams. We did this so that the mass on the periodic table could be seen as atomic mass units, the mass of an individual element relative to one another, or as a representative number, as the number of grams it takes to equal 1 mole of that atom. known as its molar mass. So the molar mass of an element is simply the masses off of the periodic table. It is the mass, the number of grams required to accumulate 1 mole or 602 sectillion or Avogadro's number amount of that element. We can look at individual elements, or more practically, we can look at a compound. Water is comprised of 1 oxygen and 2 hydrogens. So if you were to take the mass off the periodic table known as the molar mass of oxygen and add to it the molar mass of hydrogen, of 2 hydrogens, you would determine the molar mass of water, 18.02 grams. If you find 18.02 grams of water, that is 1 mole of water. That about 3 tablespoons of water contains 602 sectillion water molecules, because you have found a mole of water. Molar mass is the mass when you add up all the elements off the periodic table for that compound. If we do it for methane, methane is 1 carbon and 4 hydrogens. So if we take the mass of carbon off the periodic table, 12, and we add to it the mass of hydrogen times 4, so 4, 12 plus 4 is 16. The molar mass of methane is 16 grams for each mole. So with that being said, you can now do note quiz questions 5, 6, and 7. Pause the video and complete note quizzes 5, 6, and 7. If we know the mass of a sample, we can actually tell how many moles of that compound are present using the molar mass off the periodic table. So if I want to know how many moles of water are in 9 grams of water, I can set up my factor label method to cancel out grams and convert that to moles, because grams and moles are related by the molar mass. Since I have grams in my numerator, I need grams in the denominator so that they cancel out. And grams are related to moles by the molar mass. The molar mass is the number of grams it takes to equal 1 mole. So if you grab your periodic table and look up hydrogen, you have 2 hydrogens and 1 oxygen. So 2 times 1 plus 16 will give you your molar mass of water, which is 18 grams for every 1 mole. So 9 times 1 is 9, divided by 18 is a half. We have half a mole of water in 9 grams of water. Or going the other direction, if we have 2 moles of methane, what mass is that? We can set up our factor label method, and since we have moles in the numerator, we'll put moles in the denominator so it cancels out, and we can change to grams from moles using the molar mass off the periodic table. So for every 1 mole, there are some number of grams of methane. Methane is 1 carbon and 4 hydrogens. So that's 12 plus 4 times 1 is 16. So 2 times 16 divided by 1 is 32 grams. 32 grams of methane would be 2 moles of methane. A quick sidebar here, you will notice that I rounded my molar masses from my periodic table. Periodic tables can vary widely in what decimal place they take their molar masses to. As a general rule of thumb, I suggest you go 2 decimal places out. So for example, in the back of my classroom, I have a very large periodic table that's actually fairly accurate down to several decimal places. For hydrogen, it says the molar mass of hydrogen is 0.0794 grams for each mole, or atomic mass units. If I were to use this periodic table, as I said, I would go 2 decimal places out. So I really should have, for both of these problems, said the molar mass of hydrogen is 1.01. Again, that is just my suggestion to go 2 decimal places out. I suggest you talk to your professor and ask what they would prefer. I, in my class, will ask for 2 decimal places off of the periodic table for molar masses to be most accurate. If we're doing quick calculations like these 2 examples, using a molar mass of 1 for hydrogen is fine. You would find both of our answers to be fairly close to the answer up here. With that being said, you are able to do page 19 in your packet. Please pause the video and complete page 19. So finally, example 3 is to do a practical example. A cup of Starbucks coffee contains 36 grams of sugar. Sugar is sucrose, C12H22O11. How many molecules of sugar are in a cup of coffee? So if we have 36 grams of C12H22O11, and we want to know how many molecules that is, we don't have a conversion to go straight from grams to molecules. We can, however, go from grams to moles. Moles are the central unit of chemistry, so if you ever are stuck, you should always figure out how many moles you have. To go from grams to moles, we use the molar mass off the periodic table. So the molar mass of sucrose would be that if we added up 12 carbons, 22 hydrogens, and 11 oxygens. So for carbon would be 12.01, hydrogen would be 1.01, and oxygen would be 16, for a total molar mass of 342.34 grams for every 1 mole. And grams will cancel out, leaving us with moles of sucrose. However, the question didn't ask about moles of sucrose. It wants to know how many molecules that is, so we have to keep going. If I have moles, last class we talked about how you could convert moles into representative particles, so to representative molecules, for example. For every 1 mole, there are 602 sectillion molecules. So if I use Avogadro's number, 6.02 times 10 to the 23rd, I can cancel out moles and figure out how many molecules of sucrose are in my cup of coffee. So your factor label method allows you to get an answer. If you multiply all the numbers on top, you get 2.168 times 10 to the 25th. If you multiply all the numbers on bottom, 342 times 1 is 342. If you divide these 2 numbers, you'll find that you have 6.33 times 10 to the 22nd molecules of sucrose in your average Starbucks coffee. With that, we are now done with molar conversions. In fact, that actually brings us to the end of Unit 5. Go ahead and complete the packet pages 16 and 17, 20 and 21. Converting from grams to moles and moles to grams is a key concept in chemistry because ultimately when we are in lab, you cannot measure out moles or molecules of a substance to know how much you're putting in, but you can measure how many grams it is. So of all the things I have taught you in this class, this is the most practical. To figure out how much stuff we put into a reaction, we measure it normally in grams. So being able to convert from grams 2 moles is a key concept, and that's why I have 4 pages for you to practice this with. It also plays a key component on your SOL. That's why the next 3 note quiz questions are strictly on molar conversions. Molar conversions are their own entity on the SOL. They are a massive portion of this content. So feel proud that you now know that big step. With that being said, we are done with Units 5. We are now moving into Unit 6, Analytical Chemistry, and I will see you next time.